In this lecture, we're going to continue solving equations, but we're moving on to quadratic equations and equations that contain radicals. We're going to start with the quadratic equations. Here's a quick description. A quadratic equation is an equation that can be rewritten in the form ax squared plus bx plus c equals 0, where a is not equal to 0. The reason for this stipulation at the end is that if a were 0, then 0 times x squared would be 0, and so that first term would cancel away. And at best, we'd be left with a linear equation. A quadratic equation has to contain a term where the variable is squared. To guarantee that that will happen, we can't let a be 0. So another way to describe a quadratic equation is that it's a polynomial equation where the highest exponent on the variable is 2. With linear equations, we had one basic strategy: isolate the variable on one side. With quadratic equations, there are lots of different ways you can approach them. We're going to look at 3 different ways to do it in this video. And not only will I demonstrate the techniques, but I'll also talk a little bit about when I would use each one. The first strategy we're going to employ uses the zero factor theorem. If you want to solve a quadratic equation by the zero factor theorem, then you need to get 0 on one side, factor the polynomial on the other side, set each of those factors equal to 0, and solve the resulting equations. The name of the theorem almost tells you how you're going to approach the problem. Zero factor theorem. Get 0 on one side and factor. That's the basic idea. The logic behind this is a rule that you already know. The zero factor theorem says p times q equals 0 if and only if p equals 0 or q equals 0. So it really says 2 things. One that isn't very important to us is that if either p or q is 0, then their product is 0. Not only is that obvious, but we're not going to use that here. More important to us is the other thing that it says. It says that if p times q is equal to 0, then one of those 2 factors is equal to 0. So if we can rewrite a polynomial as a product that's equal to 0, then one of those factors has to be equal to 0. With quadratic equations, you're only going to have 2 factors, and each of those factors will be linear, so the resulting equations will be easy to solve. The example you see on the screen is a standard example of where I would try to use the zero factor theorem. It's not guaranteed to work because I have to be able to factor the polynomial. But that's the first thing I would try here. And the reason is that we already have the setup that we want in the first part. Get 0 on one side. We already have 0 on one side. This is begging me to at least try factoring. So if I can factor the polynomial on the left, then I can continue the strategy. Let's see. In order to factor this, I'm going to give myself 2 blank sets of parentheses. And the only reasonable way to get x squared is x times x. And because those x's have coefficients of 1, I can just focus on coming up with 2 numbers that multiply to negative 28 and add to negative 3. The factors of 28 I know from the multiplication tables are 7 and 4, so that seems like a good guess. And hey, those happen to be 3 apart. As long as I make the bigger one the negative option and the smaller one the positive option, they'll multiply to a negative. Negative 7 times 4 is negative 28. And they'll add to a negative. Negative 7 plus 4 is negative 3. I was able to factor this polynomial, and so now I can continue with the zero factor theorem. If you can't factor the polynomial, then you have to try something else. Here's where we use the zero factor theorem. Because the product of these 2 expressions is equal to 0, the zero factor theorem tells us that one of those has to be 0. So either x minus 7 is equal to 0, or x plus 4 is equal to 0. And now we solve the resulting equations, and I guess we could show our work, but this just says what minus 7 equals 0, so that's 7. And this says what plus 4 equals 0, that would be negative 4. And so we get 2 solutions. I won't bore you with the check every time, but let me remind you that you can check your answers to these. When we say that 7 is a solution, we're saying that if I replace every x in the equation with a 7, I'm going to get a true statement. So if I let x equal 7 in the equation, I get 7 squared minus 3 times 7 minus 28, and that's supposedly equal to 0. That's 49 minus 21 minus 28, and I'll stop there because I think you can see that that really is going to come out to 0. Let's check the other solution, negative 4. And I get negative 4 squared minus 3 times negative 4 minus 28, and that's supposed to be equal to 0. Negative 4 squared is positive 16, and negative 3 times negative 4 is positive 12, and 16 plus 12 is 28, and 28 minus 28 really is 0. Both of these check out. In this example, my first thought would be to try to use the zero factor theorem because I've already got 0 on one side and the polynomial on the left wouldn't have that many options for factoring. So it's the first thing I would try. And if factoring failed, then I would try something else. I'd use one of the techniques I'm going to show you later. Let's look at another example. Example 2 here says x squared minus 10x plus 21 equals 5. Now those of you that are good at factoring will immediately recognize that the thing on the left factors. It factors to x minus 3, x minus 7. But I don't want to factor yet because there's no rule that says if two things multiply to 5, then one of them has to be 5. That would be true if we were restricted to positive integers, but we aren't restricted to positive integers. So there are lots of things that would multiply to 5, like -1 times -5, or 10 times 1/2. That's one of the things that's special about 0. It's absolutely true that if two things multiply to 0, one of them has to be 0. That's not true for any other real number. So let's go back to the process. The process isn't called the 5-factor theorem, it's called the 0-factor theorem. So your first job is to get 0 on one side. I'm going to subtract 5 from the right side in order to get 0 on that side, and to balance that step I'm going to subtract 5 from the left side. So I get x squared minus 10x plus 16 equals 0. If we can get this polynomial factored, then we can try the 0-factor theorem. Pause the video and see if you can get it factored and finish it off. So if we're going to factor this polynomial, I'm going to give myself two blank sets of parentheses. X times x is the only reasonable way to get x squared. Because the leading term in each set of parentheses is just an x, the factoring here is a little bit easier. I'm just looking for two things that multiply to positive 16 and add to negative 10. Well, 8 times 2 is 16, and 8 plus 2 would be 10, but I need it to be a negative 10, so I need both of these signs to be minus signs. That still gives me a positive 16, because a negative times a negative is a positive, but it adds to a negative 10. The 0-factor theorem says that I can set each of these factors equal to 0 and solve. So x minus 8 equals 0, or x minus 2 equals 0. And again, these aren't difficult to solve. I get x equals 8, or x equals 2. I won't make you watch me check them this time, but let me write the check out for you. You can see that both inputs make the equation true. I want you to notice that when I did the check, I checked it in the original equation, not in any of the resulting steps. Let's move on to another example. And when you see it, you'll notice that it isn't actually quadratic. This is an equation with rational expressions. This is something we talked about in the last video. Recall, to solve an equation like this, we want to multiply every term by the greatest common factor. And to discover the greatest common factor, you probably want to factor this polynomial on the right here. So this is 3x over x minus 2. The second term is 1 over x plus 2. And that last denominator is x squared minus 4, which is a difference of squares. It factors to x plus 2, x minus 2. Well, that happens to be the product of the other two denominators, and so the least common denominator is going to be x plus 2, x minus 2. I'm going to multiply every term by x plus 2, x minus 2. That's going to cancel all of the denominators. You might still be wondering what this has to do with the current topic. Well, wait till we get this simplified. In the first term, I can cancel the x minus 2's. In the second term, I can cancel the x plus 2's. And on the right side, all of the variable expressions cancel away. So in the first term, we're left with 3x times x plus 2. That's 3x squared plus 6x when we distribute. In the second term, we're left with 1 times x minus 2. Well, that's just x minus 2. And on the right side, we have negative 4. Collecting like terms, we get 3x squared plus 7x minus 2 equals negative 4. The resulting equation is quadratic. Now, obviously, I'm going to try to use the 0-factor theorem here because it's the only strategy I've shown you so far. But why would I use the 0-factor theorem over those other strategies here? Well, I would at least try to do it first by getting 0 on one side because it's really easy to get 0 on one side. All I have to do to get 0 on one side is add 4 to both sides. The resulting polynomial looks encouraging for factoring. It might not factor, but if it doesn't factor, then our fallback strategy also requires 0 on one side. So that's another reason why I would try this first. First, I'm going to try factoring, and if factoring failed, then I'd try something else. I think this one will factor. Why don't you give it a shot? Pause the video and factor that for me. This one's going to be a little harder to factor than the previous two because the leading term isn't just an x squared, it's a 3x squared. But the only reasonable way to get that is 3x times x. And the only way we can get 2 in the back is to take 1 times 2. We just have to place it correctly. Putting the 1 in the first set of parentheses and the 2 in the second set of parentheses will give us a 6x on the outside and a 1x on the inside, and those will add to 7x. If I make these both positive, Then the constant term will be 2 when we take 1 times 2, and the outer and the inners will add 7x. Now I just set each of those factors equal to 0. I get 3x plus 1 equals 0, x plus 2 equals 0. The second one's easy to solve, that's x equals negative 2. And the first one you have to subtract 1 and then divide by 3, so you get x equals negative 1/3. And those are our two solutions. Or are they? Don't forget that we started with a rational equation. In the first fraction, we wouldn't be allowed to plug in 2 because 2 minus 2 gives us 0. But 2 isn't one of our proposed solutions, so that's okay. In the second, and in fact in the third, negative 2 is not an allowable input. Negative 2 plus 2 would give us 0. Negative 2 squared is 4, and 4 minus 4 is 0. Because negative 2 is not an allowable input, we can't actually use negative 2 as a solution. So the only solution here is negative 1/3. Negative 2 is a solution to the quadratic equation we came up with, but it's not a solution to the original equation, and that's what we're being asked to solve. Don't forget about those restrictions from previous lessons. When you choose to multiply both sides of an equation by the least common denominator, you run the risk of generating extraneous solutions, and so you have to check to make sure that your proposed solutions really do solve the original equation. Let's move on to another technique, which is solving equations by extraction of roots. This technique is distinct from the factoring strategy we just learned and the technique we're going to learn after this one, because your first step isn't to get 0 on one side. Your first step is to isolate a squared expression on one side. When you're solving an equation by extraction of roots, you're going to get a squared expression on one side and a number on the other side. You don't want any variables on the other side. Once you've isolated the squared expression on one side, you consider all cases, and I'll explain what that means as we do an example here. The example I have on the screen is a prime example for solving by extraction of roots because we already have a squared expression isolated on one side with no copies of the variable on the other side. This is why I would try extraction of roots here. The alternative would be to multiply this out by using the FOIL process, then subtract the 25 over and refactor. And that's not wrong, but it's a lot of unnecessary work because we can solve this one by extraction of roots. So we've already isolated the square expression on one side. Then the rest of the instructions say consider all cases. What do we mean by that? Well, this is saying that this expression squared is equal to 25. And there are two different ways that that can happen. We saw this when we originally discussed square roots. If you know that the square of something, I'm going to call this something u, is equal to 25, well then there are two possibilities. U could be 5 or negative 5. Those are the two cases we have to consider. I'm sure some of you recall that there's a shorthand way to write that, which is u equals plus or minus 5. It's okay to use the plus or minus notation, but I'm actually going to start with the or, because the equations are easy to solve when you write it that way. So my two possibilities are that 2x plus 3 is equal to 5, or 2x plus 3 is equal to negative 5. These resulting equations are linear. We know how to solve these. We isolate the variable term. We would subtract 3. And in fact, that's the first step in both of these. So let me just solve these simultaneously. So we get that 2x equals 2, or 2x equals negative 8. And then either using guess and check or dividing by 2 on both sides, we get that x equals 1 or x equals negative 4. You can go back and check those if you like. They do both work. So back to why I didn't use the plus or minus notation. For those of you that are familiar with it, you're like, well, isn't that a more concise way to write it? It is an easier way to write that first line because I can write 2x plus 3 equals plus or minus 5. But then I want you to solve that equation. And so if you write 2x equals negative 3 plus or minus 5 when you subtract 3 from both sides, and then divide by 2, you have x equals negative 3 plus or minus 5 divided by 2, but those can be simplified. That's negative 3 plus 5 over 2, and negative 3 minus 5 over 2. And you can do that arithmetic. Negative 3 plus 5 over 2 would be 1, and negative 3 minus 5 over 2 would be negative 4. And you get the same solutions, but to me that's a bigger mess than's necessary. The plus or minus notation is really useful in two scenarios in my opinion. When you can't simplify anything, or as a part of the quadratic formula, which we're going to look at later. Let me show you a couple more examples here. In example 2, we have 3x squared minus 48 equals 0. And this one looks like it's primed for the zero factor theorem. You can factor the left side. There's nothing wrong with that. But what calls out to me is that I could easily isolate this x squared term by adding the 48 to both sides. I'm not saying that's best. That's what I see. That really stands out to me. I get 3x squared equals 48 from doing that. And then I could divide both sides by 3. And I get x squared equals 16. Now I just consider all cases. If x squared is equal to 16, then x is either equal to 4 or it's equal to negative 4. And here I have no need to simplify anything after that. Those are my two solutions. So I would just write x equals plus or minus 4. But of course you could write x equals 4 or x equals negative 4 because it means the same thing. In the next example, I'd use the plus or minus notation, but for a different reason. I have the square of a binomial equals 13. This one is primed for extraction of roots. But the problem is that 13 isn't a perfect square. So when I go to find the square roots of 13, well, here I can't do any better than the cases u equals the square root of 13 or u equals the negation of the square root of 13. That radical doesn't simplify in any way. And because it doesn't simplify, I would just write this as plus or minus the square root of 13. For those of you that have seen this technique before, that's probably the first step you're used to seeing, is rewriting it with a radical on the right side and then a plus or minus. You'll notice I don't write that step unless I can't get it to simplify. Now I know this looks ugly and maybe that makes you a little bit hesitant to solve it in the regular way, but the square root of 13 and the negation of the square root of 13 are just numbers. So how would you solve it if there was any other number over there? In fact, let me get rid of this for just a second. If it said x plus 7 equals 2, or x plus 7 equals negative 8, or x plus 7 equals 1/2, you wouldn't hesitate, you'd subtract 7. Well, the square root of 13 and the negation of the square root of 13 are just numbers as well, and so we're still going to subtract 7. The standard way to write this is with that negative 7 to the left of the plus or minus rather than putting it behind the radical. So we would usually write negative 7 plus or minus the square root of 13. That does mean negative 7 plus root 13 and negative 7 minus root 13, and if you want to write it as two separate statements, that's perfectly fine. But because this doesn't simplify, I would use the plus or minus notation. So there are three examples where I would use extraction of roots. Before we move on to the last technique for solving quadratic equations, let me show you an example that looks like it's set up for extraction of roots, but really isn't. This example says x squared equals the negation of x plus 6. And we have the quadratic term isolated on one side, so can't we just start with extraction of roots? We can't because there's a variable on this side. So how would you solve this equation? Well, my first thought would be to try moving everything to one side, getting 0 on the other side, and trying factoring. X squared plus x minus 6 equals 0. Oh, okay, yeah, this is x plus 3x minus 2. And so I set each factor equal to 0. And the solutions pop right out. Extraction of roots doesn't work here because your first step would be to write x equals plus or minus the square root of the negation of x plus 6, but now you've trapped this x underneath the radical. You're not going to be able to dig it out of there. You can't add x to both sides to get it out because it's underneath the radical. So that won't work. So just because you see an isolated squared term on one side isn't enough. You'll notice in all of our examples the other side was a number. Here we had 25. In the last two examples, we had 16 and 13. If you have a constant on the other side, you're good to go. If you have a variable on the other side, you need to try another technique. There's one technique that works no matter what. It might not always be the most efficient way, but it's guaranteed to work. It's called the quadratic formula. It says if ax squared plus bx plus c equals 0 with a not equal to 0, so that you're guaranteed to have a quadratic equation, then the solutions to the equation must be of the form negation of b plus or minus the square root of b squared minus 4ac all divided by 2a. Notice that a can't be 0 here either because you'd be dividing by 0. The beautiful thing about the quadratic formula is that it's guaranteed to work. The drawbacks to the quadratic formula are remembering it, being careful when you plug in all of the numbers, and it might not be as efficient as the other two options because sometimes factoring is really easy, or sometimes expanding everything to get it into this form can be a pain. Sometimes the quadratic formula is a really efficient way to do a problem. Sometimes it's kind of a roundabout way to do it. I'm going to demonstrate both. So in our first example, the quadratic formula is the best way to go. It says 3x squared plus 10x plus 6 equals 0. Now my first thought would be to try factoring here. So I would try factoring first. And let's see, I do 3x times x to get the 3x squared. And then I have to break up the 6. Well, 1 times 6 isn't going to work because that's going to give me 19x. And let's see, there's 2 times 3, that's 11x. That was close, but not quite. And if I do 3 and 2, well, that's definitely not going to work because I could pull a 3 out of the first set of parentheses. 6 and 1 is the last guess. That doesn't work either. That gives me 9. So this doesn't factor using integers. So I'm not going to see how to factor it. It's not easy to write one side as a perfect square. It can be done by completing the square, but again, it's probably not worth the trouble, especially if you know the quadratic formula. The quadratic formula generates the solutions just by following this formula. In order to start, you have to have 0 on one side. You have to have it in the standard form. Once you've done that, you just have to follow the formula. So let's see, it starts with the negation of b. We get negative 10, then it's plus or minus. There are two solutions here, plus or minus. The square root of b squared minus 4ac. So the square root of b squared, it's 10 squared, minus 4 times a is 3, times c is 6, all divided by 2 times a. So that's 2 times 3. And so that's negative 10 plus or minus the square root of 10 squared is 100. And 4 times 3 times 6 is 12 times 6, that's 72. And that's all divided by 6. And that's negative 10 plus or minus the square root of 28 over 6. To me, this answer is acceptable. You could stop here. However, this radical can be simplified a little bit. And so just to remind you how to do that, the square root of 28 can be rewritten as the square root of 4 times the square root of 7, and the reason we would do that is that the square root of 4 is 2, so that's 2 root 7. And now we can reduce everything by a factor of 2. In the age of the calculator, I don't think there's anything wrong with this as a final answer. The only reason I think you should simplify further is if the number under the radical is a perfect square. Then of course you should simplify, because you're going to get rational solutions. But if your answer is going to have a radical in it anyway, then I don't see any reason to do the rest of this. It would be just as easy to approximate these two solutions, and there are two answers there because of the plus or minus. It would be just as easy to approximate these two solutions with a calculator as it would be these two, and I don't have to do the extra work to get there. So I'd be okay with you stopping here. I don't think it's necessary to take it to that last step. Let's do another example. This one says x squared equals 3x plus 7. And we discussed this before, but I just want to talk about it. It looks like it's set up for extraction of roots because we have an x squared isolated on one side, but unfortunately there's an x on the other side. And because we have variables on both sides, extraction of roots won't work. Instead, I'm going to move everything to one side. X squared minus 3x minus 7 equals 0. And those of you with lots of factoring experience will notice that this doesn't factor. You can just feel it. There's no way it's going to factor. You might try first, but I wouldn't spend more than, say, 15 or 20 seconds trying to factor something when you've got the quadratic formula in your back pocket. You know the quadratic formula is going to work, so don't waste your time. If you can't see how to factor it fairly quickly, just use the quadratic formula. So let's see, we start with the negation of b. That's the opposite of negative 3, which is 3. Plus or minus the square root of b squared minus 4ac. When I square negative 3, I need to put it in parentheses. Negative 3 squared minus 4 times 1 times negative 7. c is negative 7. All divided by 2 times a. That's 2 times 1. Implied coefficient on x squared is 1. So I simplify and I get 3 plus or minus the square root of 9 plus 28, all divided by 2. Which is 3 plus or minus the square root of 37 over 2. The square root of 37 doesn't simplify in any way because 37 is prime, and so I wouldn't take this any further. There are two solutions there. There's 3 plus the square root of 37 over 2, and there's 3 minus the square root of 37 over 2. A lot of people want to use the quadratic formula every time because it's guaranteed to work. And while that's true, it's not always the most efficient way to do it. We're going to solve the following equation using all three methods that we've discussed. I'm going to do them from the way that I think is best to the way that I think is worst. Best here, I think, is extraction of roots. This one's begging to be done by extraction of roots. I know that if x plus 1 squared is equal to 36, then x plus 1 either has to be equal to 6 or x plus 1 has to be equal to negative 6. Those are the two cases. I would not use the plus or minus notation here. because I can simplify. If x plus 1 is equal to 6, then x is equal to 5. If x plus 1 is equal to negative 6, then x is equal to negative 7, and I'm done. To do this with the zero factor theorem, or to do this by the quadratic formula, I would have to get 0 on one side. Most of us would probably expand this first. So let me expand here. X plus 1 times x plus 1 equals 36. That's x squared plus 2x plus 1 equals 36. And then I would subtract 36 from both sides and get x squared plus 2x minus 35 equals 0. Once I got here, I would try factoring, and it turns out that this does factor. This is x plus 7 times x minus 5. And so x plus 7 equals 0, or x minus 5 equals 0. And so I get x equals negative 7, or x equals 5. Same two solutions. A lot more work, though. If I were to do this by the quadratic formula, I'd have to do the exact same expansion. I'd still have to get 0 on one side. But now I'd have to apply the quadratic formula. So that's x equals negative 2 plus or minus the square root of 2 squared minus 4 times 1 times negative 35, all divided by 2 times 1, which is negative 2 plus or minus the square root of 4 plus 140, all divided by 2. That's negative 2 plus or minus the square root of 144, all divided by 2. 144 is a perfect square. I have to split this into cases. So x equals negative 2 plus 12 divided by 2, or x equals negative 2 minus 12 divided by 2. Negative 2 plus 12 is 10. 10 divided by 2 is 5. Negative 2 minus 12 is negative 14 divided by 2 is negative 7. And I get the same two solutions, but you can see that was a very inefficient way to do the problem. It was even worse than factoring, unless you just couldn't see how to factor that. If your factoring skills are still rusty, then factoring might be the worst way for you to do it. For me, the worst way is this quadratic formula. So this is why you want to assess the situation before you proceed. If you can easily write the equation as the square of some expression equal to a number, try extraction of roots. If you can't, get 0 on one side and try factoring. If factoring fails, then try the quadratic formula. That's my advice. The other topic we want to cover in this lecture is solving equations with radicals in them. To solve an equation with a radical in it, you want to isolate the radical on one side, raise both sides to the appropriate power, that is, raise it to a power that will get rid of the radical, that will undo the radical, and then solve the resulting equation. You'll have to check for extraneous solutions when you raise both sides to an even power. Here's a standard example that's already set up. We've got the cube root of the binomial 2x plus 6 is equal to 3. I want to get rid of that cube root. That's what's making this problem difficult to solve. Well, to get rid of the cube root, I'm just going to cube both sides. I'm just going to raise both sides to the third power. The point behind this is that when you cube the cube root, they undo each other, and I'm just left with 2x plus 6. And on the right side, I just get a number. 3 cubed is 27. The resulting equation is linear, so we're going to isolate the variable on one side. I'm going to subtract 6 from both sides. 2x equals 21. I divide both sides by 2. Then I get x equals 21 over 2, or 10.5. And that's our solution. I know I said you need to check for extraneous solutions, and we should always check our answers. But you don't really need to check for extraneous solutions when you raise both sides to an odd power. It's when you raise both sides to an even power that you need to be careful. Like in this example. Example 2 says x minus the square root of 3x minus 2 equals 4. So I'm going to isolate the radical on one side, and I would personally do that by moving it to the other side and subtracting the 4. If you're wondering why I would do that, it's because I want to leave the coefficient on my variable positive. I feel more comfortable that way. It's definitely not necessary, that's just my preference. Once we've isolated the radical on both sides, we raise both sides to the appropriate power. Well, this is a square root, so we're going to square both sides. When you square the side, you're squaring the entire expression. So when you square the left side, you're not squaring the x and squaring the 4, you're squaring x minus 4. You're multiplying x minus 4 by itself. On the right side, the square and the square root undo each other, and we just get 3x minus 2. We multiply this out using FOIL. In the interest of time, I'll just come up with it. It's x squared minus 8x plus 16. And now we have to decide how we want to approach this. It doesn't seem like there's going to be an easy way to write this as a perfect square without variables on the other side. And so I would get 0 on one side. I would subtract 3x and add 2. I would subtract 3x and add 2 in order to get 0 on the right side. So that's x squared minus 11x plus 18 equals 0. That does factor. That's x minus 9, x minus 2. If it didn't factor, I'd use the quadratic formula, but this factors. And so I get two proposed solutions, x equals 9 or x equals 2. And I emphasize proposed in that annoying way because I have to check to make sure these really work back in the original equation. It is possible that both of these work. It's possible that neither of them work. We've got to check. I can't spare you the work this time because I have to talk you through it. So let's check them both. If I check x equals 9, I get 9 minus the square root of 3 times 9 minus 2, and that's supposed to be equal to 4. Well, 3 times 9 is 27, and 27 minus 2 is 25. And remember, this notation means principal square root. The principal square root of 25 is 5, so this is 9 minus 5 equals 4. And yeah, that's right. 9 works. Let's try 2. This is 2 minus the square root of 3 times 2 minus 2, and that's also supposed to be equal to 4. Well, that's 2 minus the square root of 6 minus 2 is 4. And the principal square root of 4 is 2. So this is 2 minus 2 equals 4. No, that's not true. 2 minus 2 is not equal to 4. So 2 doesn't actually work. That extraneous solution was generated because we squared both sides. Anytime you choose to raise both sides to an even power, you've got to check for those extraneous solutions. The only solution here is x equals 9. So we got the radical on one side, moving everything else to the other side. We squared both sides to get rid of the radical, and that's where we run into the issue of generating extraneous solutions. We've got to be careful. The resulting equation was quadratic, so we got 0 on one side. We factored. We solved the resulting equations. And you'll notice this time out of instinct, I skipped the step of writing x minus 9 equals 0 or x minus 2 equals 0. You probably already skipped that anyway, so I'm not too concerned about that. Then when I got those proposed solutions, I checked them. I didn't check them because I was worried I made a mistake. I checked them because when you square both sides, you must check for extraneous solutions. If you have any questions or just need to see more examples, you can come see me during an office hour or send me an email.